Hello. Hello, am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So I think everybody has successfully submitted the last assignment by Sunday, right? So we'll just go on with a bit more complex assignments. So before we do that, just we'd like to ask you if everybody understands, I mean, inside, if you are programming in SPIM, what is the role of a stack pointer, a frame pointer, and where is the stack segment located inside the SPIM simulator? I mean, I mean, when it is emulating the mixed microprocessor, how is this stack emulated? So can anybody tell me what is the, I mean, how is the, I mean, stack pointer and frame pointer are related and what is their function? Aditya Agarwal, are you there?
Yes, sir.
Yeah, please answer.
Sir, I'm not sure about the frame pointer, but the stack pointer is used to store the arguments and while doing a function call.
Okay. Anurad Bhattacharya.
Yes, sir.
Yes. Can you tell me what is the frame pointer?
So, as far
You are
as
not at all audible.
so, am I audible now?
Very low pitch.
Okay. So now,
Anyway, that saves you. Yeah, now we can hear. So if you can just tell us.
sir, so you asked about the meaning of stack pointer and frame pointer
Frame.
in terms of SPIM. That I could not actually get what you exactly meant.
In general, I mean,
of,
when you are doing programming on a computer, you know there is a stack pointer and there may be always also a frame pointer. If anybody has heard of what is the frame pointer.
I had read about it. I cannot actually remember frame pointer. As far as I know.
Anybody else?
Sir, this frame pointer marks the start of the current frame,
Who
and
is
the stack
this?
pointer.
Deep. Okay. Yes,
Yes, sir.
please. Yes, please, Deep.
And
Go ahead.
and the stack pointer marks the end of the frame
So then you
in the
mentioned this
current
word
frame.
frame, right? So what is this frame? And what is the role of a frame?
The frame basically indicates a portion of the stack that is usable by a function. So the first part will usually contain the return address, then the arguments, and then or whatever variables are stored on the stack. So a frame indicates a portion of the stack that is used by a function,
Okay.
or rather
Anybody
a
else?
function call, or rather
Yes. Thank you. Thank you, Deep.
during.
Anybody else who would like to pitch in at this point and tell me why this is required? Just from common sense. So he has given a correct definition. What he is saying, let me just summarize. He is saying that suppose a function is called, right? So then let's understand the I mean issues that may happen when you are calling a function. A function may have too many arguments, right? So it is not conceivable that you pass all the arguments through some pre-specified registers, that you say that, well, this argument would be in this register, argument a0 in registers r0, argument a1 in register r1 up to n, where n is very high. It doesn't make sense because the register file may have many other uses, right? So I mean, the nicer way of doing the programming is that you have a fixed, I mean, as a small upper limit on the number of arguments you will like to have on registers. Why? Because, well, if you just populate registers with too many arguments, then there won't be many registers free for doing the temporary variable allocations while you are writing, while your actual program function is executing, right? And that's counterproductive towards speed and efficiency of your code. So you don't really want that to happen, right? So the convention would be that you have a few of the arguments in the register, and the rest of the arguments you will like to push in the stack, right? Considering a very complex function or procedure you are going to execute, right? So when you are really going to execute this function, as per this defined convention, you will push some of them to the stack, and then of course anything else that you want to remember in the stack before before you really jump onto the function and execute. Anybody? You have pushed some of the arguments, so you are going to work with those arguments. Anything else?
We need to access the variables using the frame pointer, like that serves as a base pointer.
Okay. Anything else?
Return address.
Right. Why do I need the return address?
Because the array pointer might change by calling subroutines in the function.
Right. So typically we would like to have it, right? So overall, it seems that when you are going to call into a jump into a procedure, it may require many positions in the stack, right? Now, if I require many separate locations in the stack for one procedure, I have to also think when I am trying to design this system, or I am trying to design this entire architecture of assembler, loader, and linker in the system, that how do I manage consecutive calls, right? Because a function f1 is called from main, f1 calls f2, f2 calls f3, like that. I can have a arbitrary chain of function calls happening, right? And my runtime system has to actually ensure that when the last call terminates, that there is a correct return sequence which is being executed and everything occurs safely, right? That means when the lowest level function returns, its output is viewable to the immediate the callee function. So every caller callee relationship has to be nicely preserved, right? I mean, some of the variables would be shared, so those have to be visible to the caller. Some of the variables are not shared, so those should not be changed by the caller, by the callee. All these things need to be very safely managed, right? So the nicer way of implementing that would be that you think of every current function calls activation record to be stored in the stack. So you follow a convention that when the call is made, some of the arguments may be passed through registers, but most of the arguments are pushed into a stack, and you define a space in the stack called the stack frame for this current call. Well, so this is going to contain basically the context of this function. That means the arguments that is going to use, things it may produce, return address, and other stuff, right? So this is what we call as the stack frame, and the reason we will like to have it is because this function during its ongoing call may make another call, right? So right now when the stack frame of this function is active, I may need to accommodate more number of stack frames, right? So that motivates us why I need multiple a method to have multiple stack frames in the stack, right? Now, since I will require these stack frames, I need a way to denote this boundary of the frames, right? And this is what is basically done by the frame pointer. So for one stack frame, I will have this frame pointer which is pointing to the first word in the currently executing procedure stack frame. Okay, so you have the arguments pushed, and then the stack frame would start for this current point, this current procedure, right? And the stack pointer will point to the last word of the frame, right? So that means if I am making another call, for that I will again save this current call stack pointer, frame pointer, and initialize them to newer areas of the stack to define these new calls stack frame again with updated values of frame pointer and stack pointer, right? Now, of course, if you are doing it as assembly, you have a lot of freedom. You have to identify what are the things that you need inside one instance of a stack frame for a caller function, and accordingly you will choose a frame size, right? Accordingly, because based on the frame size, it will depend how much of the frame pointer you are going to update and all that, right? So what we'll really like to do in this week's assignment is we like to have one program where you make usage of the stack. So the different possible memory locations where that you are having you are going to have in this MIPS system is you have a memory heap store and you have a memory stack, right? So by default, when you are trying to do some memory allocation, it will happen. So let's say you are making a malloc type call or the sbrk call in MIPS assembly. It is basically growing inside the memory heap store, right? So that's something you don't have to manage, right? It will just increment. The heap will go from the bottom to the top, and the way the address space is arranged here, the stack will grow from the top to the bottom. That means if you are defining a stack frame, the stack pointer values are going to increase, right? So that's what it is. Any more details or some example programs? I think we have some very nice examples. If you look into this combined SPIM PDF that we have actually added in this in the resources channel of this course, right? So here you have a picture of the memory layout. So as you can see that you have this stack segment growing downwards, right? And here you have, for every program that you are running, you have this well-defined positions of the text segment where the dot text part is going to be allocated, the data segment where your dot data part is going to be allocated, and whatever you have in your program in the dot data part that you specify is going to be in the static part, and after that further allocation would be done in the dynamic part, right? So that's how it works. And then when you are making these program calls, you will have this issue of stack coming up, and accordingly, as you can see, so we have an example of a factorial program executing. So every call is actually storing its old value of return address, stack pointer, and frame pointer in that way. Okay, so that's how the stack is getting managed, and we also have several nice examples here. So I mean, you can just have a look into this. So based on this, let's just float today's assignments, quite easy ones, I would say. So the first one is a simple one. So everybody remembers Booth's multiplication algorithm. It's a hardware efficient multiplication algorithm, which must have been covered in your switching course.
No, sir, it was not covered.
It was not covered.
No, sir.
Okay, we had such a idea that it may not have been covered. So what we have done is we have provided you a flowchart based method technique of the Booth's multiplication algorithm. But what we have not provided you is the reasoning and the material which shows that why and how this is really efficient. So we will then do that as part of this lab, because I think that this is really a very important algorithm about how multiplication is implemented in hardware. So we should really understand that why this is a very efficient algorithm. So for the time being, let me just walk you through how the what you are supposed to do. So you will just enter two numbers. Note that we are assuming that the numbers are already in 2's complement form. So we are going to basically multiply signed binary numbers, assuming that they are given in the 2's complement form. And the multiplication should be done in using this Booth's multiplication algorithm, and the results has to be given. So we'll just look at the flowchart for the time being, and later on we'll provide you some more elaborate material, because the whole thing was made under the assumption that this very standard algorithm has been done. So you have the multiplier and the multiplicand, which are sitting in these two arrays, let's say M and Q, these two registers, okay, in 32-bit format. Fine. So we are again, as I said, that we are assuming that these are given in the 2's complement form, right? So what we are going to do is initially, so let's say this multiplier is of size, I mean 32-bit, right? Let's say I'm just making an example here. So it's starting from Q31 up to Q0, right? Q0 is the LSB. So when you initialize, you put in an additional value Q minus 1. That means what? You add some 0 bit to the left of the LSB. Why will be very soon clear to me. Okay. Now what we are going to do is, so you just see what are the last 2 bits of your multiplier. Okay. So you already had the last bit, the LSB, and you have added one bit extra, 10, at the right hand side of the LSB. So it's like the new LSB, right? So what you do is you just see what is the value of this combination of 2 bits, right? So you have 3 possibilities, 0, 0, 0, 1, 1, 0, and 1, 1, right? If it is 0, 1, then all you do is you add m, this multiplicand, with an initial with a register containing an initial value of 0, right? So we are talking of this in terms of a hardware algorithm here. You have to translate it using into a MIPS assembly where the working principle would remain same, right? That's the job here. So in Booth's algorithm, what is being done is, if this last 2 bits is 0 and 1, then you are just storing this m in this variable a. Okay, that's all you are doing. Now, after that, what do? You do a arithmetic shift right, right? So for all these variables a, q, and q inverse, you do an arithmetic shift right. So if I do an arithmetic shift right, what happens? Hello? Anybody? So you have a value.
It gets divided by 2.
It gets divided by 2, right? So
Yeah.
in this case, what will happen? This content of A, which is right now nothing but the multiplicand, it's divided by 2. And you are shifting this Q, the entire Q and Q inverse. That means what? Earlier what was Q0 becomes Q minus 1. And earlier what was Q1 becomes Q0, right? As simple as that. Hello?
Yes, sir.
Okay. So then essentially what we are doing, we have done what is to be done for the last pair of values. Now we just want to slowly scan through this number, which is the multiplier, from the right to the left, right? So for doing that scanning, we are just simply doing this arithmetic shift right inside the loop, right? So once I do that, what's going to happen is, I mean, the older Q0 is now the Q minus 1, the older Q1 is Q0. So you come back here again in the loop and again check, right? So again, if it is Q01, you do this A equal to A plus N. If it is A10, if this is 10, then all you do is A is nothing but A minus N. Earlier, whatever you was doing is you was doing the addition. Right now, what you are doing is, sorry, earlier you were just adding up the content of A with M, but if the content is, instead of 0, 1, it is 1, 0, you are just subtracting M from the current content of A. Okay, in that way you are updating this A, right? And for the other combinations, that is 1, 1 or 1, 0, you don't change the status quo, right? So this loop continues, and with this loop, I mean, this will continue for this N, considering that these are basically N bit values, right? Given in this 2's complement sign, right? By the way, here you see we are considering two 16-bit signed numbers, so that the final value is encodable in 32 bits, right? So you have to implement this in a multiply booth procedure, and all these things are given, that which registers are supposed to contain the input arguments and where should the output argument come and all that. Now coming back to the procedure. So as we can see, all that we are doing is this multiplicand and multiplier, they are there. This multiplier, we are slowly scanning through this from the right to the left and checking the last 2 elements always, right? And again doing that right shift and then again checking the last 2 elements. So essentially we are scanning from the right to the left, considering a pair of consecutive elements together, and based on their values we are doing this addition and subtraction. So it seems like a very simple thing, right? Because if you think what is the complexity of this loop, right? So this loop, you are going to do as many shift operations as is the number of bits there, right? So it's basically n number of times, right? N number of times you go through this, and then in each of these for each of these shifts, what is the operation you are doing? You are either doing a binary addition or you are doing a binary subtraction, right? So you have quite a I mean, the total number of operations you are doing is simply a number of shifts, which is same, which is in the order of the number of bits that you have, and a similar number, and in the worst case, a similar number of these additions or multiplications. And with that, you are able to achieve the entire multiplication of these two n-bit numbers, right? Now, it can be actually shown with a proper analysis that this is going to take a significant less number of arithmetic operations than the standard multiplication algorithm for binary numbers, right? Because what does the standard multiplication algorithm do? It will check each of the bits of the multiplier individually and accordingly do the addition and shifting, right? But here you are doing pairwise, and with overall all these things, you can show that this is a much efficient algorithm. So you have to implement this in MIPS assembly. So that's the first task. And the second one is basically implementing sorting in MIPS assembly. So what this one asks you to do is you take as input an array. So please read through this specification very clearly. It tells you to do certain things, to implement certain sanity checks and all that, right? For example, you should not store the number as scalar in 10 different non-contiguous locations, right? So you have to store it like an array, right? So you take an input such a kind of array, and you are supposed to figure out what is the kth largest element. Before figuring that out, you should just sort the array and then report the kth largest element, where this k is one of the user inputs. For sorting, you have one of the very standard sorting algorithms given. You are asked to implement this sorting algorithm only, right? So it's simple. The first program you should write is, anyway, this is then I was thinking whether to not give one of these problems because, well, this multiplication algorithm you may have implemented in switching or somewhere. So, but since that is not done, well and good. It's nice that you will implement this algorithm in MIPS assembly, and then the second problem would be that you figure out what is the kth largest. Why, fine. And then the third problem is somewhere where we like you to explore this issue of stacks. How to store data in stack and how to work with data in stack. So here, what all you are going to do is, well, you are going to do a matrix transpose operation. So you will input these 4 positive integers, okay, m, n, a, and r. So you will then allocate space for an m cross n integer array A and another n cross m integer array B onto the stack, okay. So finally, what we want is B should be a transpose of A, but right now you have taken as input these arguments m and n, and you have to allocate the space for them in stack, right? Now then you will populate the array in a row measure fashion using a GP progression series with initial value A and common ratio R, right? So you will just evaluate the GP progression series with respect to these two parameters, and accordingly your program should populate the array A. So mind that this thing is located in the stack, right? And the populating all the entries of A has to happen in the stack. Then you just print the elements of stack A, and then you should store the transpose of A in the space that you have already reserved in the stack for locating B, right? And then finally you print the elements of B. So we are proposing that you do all the above by with the help of some individual functions, right? So you implement a init stack function which will initialize stack and frame pointers. You implement the push to stack function which takes a parameter and it will push it to a stack, right? I think it's better to fix up a register from which this push to stack function is expecting this parameter. So maybe after this lab, we'll just modify this statement a bit, and we'll fix up the register from this. From which it can expect this push to happen, right? Okay, and then we have you have to implement this malloc function. So again, this malloc function is going to allocate memory on the stack. Any idea how this can be done? Anybody? How am I going to implement a malloc function which will allocate memory onto stack?
Can you syscall with vi equal to 9?
What syscall with?
The
thing that you have to choose is the ninth one, the ninth instruction type.
Yeah,
It's-
that is for allocating malloc in dynamic memory allocation in the heap segment. Here I am asking you, so that's basically the malloc that is given, right? Here where you asking you to create your own malloc function, which is going to allocate things, I mean, allocate memory in the stack. Anybody?
Subtracting the stack pointer by that amount.
Exactly. All that means is you have to remember. See, I mean, you are designing the malloc function, right? That means you have a lot of power. You are told that you are going to design the malloc function to allocate memory on the stack. So you as a designer know that, well, this is my stack frame. The stack frame is going to start from here. After that, these are the positions where I may be having some other values, right? So how is this malloc going to work? This malloc you are going to call with a parameter size, right? Now, what is this malloc going to reply back with? Is going to reply back a return address, the starting address on the stack from which you are entitled to have free space up to parameter size, which can be used for the purpose, I mean, or for whatever you want this, you have called this malloc, right? So that simply means you have to remember that, well, what is the start, right? From which the, I mean, this function, I mean, because that is something that the function is going to return back, right? Through some register maybe to your procedure. And then all you need to do is you have to increase the stack pointer. Basically, since the stack is going lower into the memory, so you have to decrease the stack pointer up to that malloc size, right? Because right now that is the amount of memory then which you are allocating in the stack for this malloc call. So that's how your malloc function should be designed. Is this clear? What we are trying to say? Please understand. This is, I mean, otherwise we would not have asked to design a malloc or something. We want you to think that how your own malloc function is going to allocate or deallocate memory on the stack. So it's basically going to happen inside the one stack frame of the current procedure by increasing or decreasing the stack pointer. Are we clear on this?
Yeah.
Yes, sir.
Shomujit, this is RSC here.
Yes.
Yeah.
Yes,
so
please.
this malloc function, are you expecting this SBRK or those type of system calls? I mean, in
No. It is not required. It's just stack manipulation.
Then how will? So malloc you are okay. So okay. So basically you are
Rajat, I cannot hear
so
you.
basically you are simulating dynamic memory allocation using normal available stack memory, is it?
Right. Just by
because
remembering,
I mean,
just by modifying the stack.
there are this memory allocation system call type instructions in MIPS, and those are also supported by SPIM to a certain extent, but we have not taught it in class.
Yeah, I know that is using SBRK and all that, but we are not going into that actually. This is just with stack. I want them to play with stack. That's
because the students would probably have this question anyway. So
right,
okay,
right.
fine then.
Yeah. Anyway, thanks for the question, Rajat, because some of them may also be thinking in respect to normal.
Yeah, they would have asked this definitely.
Yeah, no, sir. Somebody actually asked in between also. So because we could have used this, so we are actually specifying that. I mean, actually replying to that only. That I mean, we are doing a very simple thing here. You are going to have your own malloc function, which is going to allocate memory on the stack by suitable modification of the stack pointer movement, okay, inside the current stack frame. So that is something you should do. And the other functions that we will implement are very standard ones for basically a print function for printing the matrix, and the original transpose the function Now this is a function which is going to do the okay, let me just walk through print matrix and transpose matrix in more detail. So as you can see, the print function will take 3 parameters, right? The positive integers m and n, an address of 2-dimensional m cross n integer array A, right? Because as we have said that this is a row, this is m cross n is a 2-dimensional array, but it's in a row measure ordering and it's going to be stored in the stack, right? So this is going to take these arguments m, n and the starting address of this array, right? And from that it should be able to print all the elements of A in a row measure manner, right? So that would be a helper function you should design. And finally you have this transpose matrix. So this function takes positive integers mn and the address of 2 integer arrays A and B, mind you, which you have already allocated on the on this stack, right? A is of size m, I mean both are of size m cross n. It's just that they are column and row are, one is m and n, another is n and m respectively, right? Now this is what is going to compute because A is already initialized through that GP series, right? A is already initialized with that GP series, and then this transpose matrix function is going to receive A and B's base address. It is going to walk through A and take the values and accordingly populate B in such a way so that B is the transpose of A. Everybody must be knowing what is a matrix transpose, right? So in this way, using these helper functions, you should be implementing this program which computes matrix transpose, but all the IOs happen just on the stack. So everything, the entire memory management has to be done using suitable saving of context of the stack pointer and movement of the stack pointer. So this is a bit this may seem a bit initially difficult. So what I would really ask you to do is read this material that is there, right, which we have provided you in this combined spim.pdf, this material, and here how the stack is basically organized and how the stack elements are going to be saved, all those things are provided in detail. And I think if you just refer to one of the programs that is there, for example, this factorial program, it will help you to understand how the stack thing is working, and maybe for this assignment and also for recursive assignments which we are going to float next week on the week after that maybe. Okay, so just go through this appendix document, just this part where they talk about stacks and stacks frames, then it will be very easy for you to just implement this idea of memory allocation using stack and storing matrices and transforming matrices on the stack. Okay, actually very easy. It's just that instead of in the heap part, you are working on the stack part. So you have to think like that. Any question from anybody?
So do we also need to take care of memory alignment while allocating memory on stack?
Yeah, sure.
Okay.
Excuse me, sir.
Yeah.
Sir, actually, I saw that the deadline for this assignment is this Sunday itself. But I would like to request for an extension till like 17th of September, next Friday, because sir, we have our tests this week till Friday.
This is the exam week, right?
Yes, so this is the exam week, and plus we have a few assignments due next week as well in other subjects. So if you could possibly extend this till next Friday.
Okay, what you do is assign the first 2 assignments you submit by Sunday. The last one you submit by next Wednesday. Okay, I think that is fair enough.
So then.
So like, how will submission work? Like, we are allowed to only submit one file. So will we be deleting our previous 2 and then submitting the one again? Like,
that is a clerical thing which we will resolve. We will have assignment 2.1, 2.2, 2.3.
Okay, got it. Sir, till when can we expect the evaluation of the first two assignments?
In another week's time.
Also, sir, I wanted to ask, will we have a lab quiz for this course, and when can we expect it?
These things we will discuss. I mean, we will provide you a suitable announcement. Things are a bit lucid. We are trying to see how things are shaping up, how you are, I mean, doing these timely submissions and all that. We will discuss.
Okay, sir. Thank you.
Rajat, you want to take this question?
What is the question?
He is asking whether we will have a separate lab quiz apart from assignment submission.
Last year we had one lab test towards the end of the semester, but it was not on any programming assignment. It was basically like a question paper type of test. I mean, they were asked to solve problems from computer organization mechanisms. I don't remember exactly what was the content, but I think I remember there was no programming aspect that test. But there was one test. That is good because it helps to differentiate the marks, because here we are having a group-based submission. Both the group members get the same
right.
marks for every assignment, irrespective of how much effort they have individually put in. But in the lab test, because it's a individual test, it is better. I mean, we can either we should have one lab test at least, and it can either be a real-time assignment-based test, or it can be like a class test kind of a thing. We'll see.
So we will have that maybe around the fag end of the semester.
Yeah,
so
towards the end of the semester, yes. Because
so you expect one test apart from the regular weekly submissions that we are
there
having.
will be one test probably, and that test would last year I think it had 40% weightage, so substantial weightage to make sure that the performance in that test is important. So maybe this year also we'll have something like that.
We will have a test for sure. We will have a test.
We will have a test for sure. Yes, not this week. Some of you have sent me emails that there are many tests happening this week. See, if we have not declared any test in advance, we will not have a test just like that surprise test kind of a thing. That will not have. So if it has not been declared, definitely it would not be this week. Okay. But we will have a test at some point. You will be given prior intimation, the syllabus, everything will be informed to you. Just like you wrote your theory class test on Monday. Similarly, before the lab test also, we will give you sufficient amount notice, at least 1 week notice. Okay. Okay, thank you.
Excuse me, sir.
Yes.
Sir, again, I'd like to request at least if you could extend our deadline for all submissions till Wednesday. That would also be really helpful because, especially, sir, we've not done Booth's multiplication algorithm also, and then there's other things to read up on as well.
Okay, fine. Then everything you submit in one file on Wednesday.
Thank you so much, sir. Thank you so much.
Let it be at least before the next Wednesday class. Okay, so maybe
Booth's
Tuesday.
algorithm would be taught to you. If not this week, possibly next week. I think it will be taught. Professor Bhattacharya will teach it.
So fine, then it is also resolved. Yeah. So okay, you have time till Wednesday midnight. I think that would
All
be.
right. All right, sir.
Okay. Any other query? So I hope everybody has submitted the previous assignment, right? Which was quite easy one. Okay. Aryan Singh, you have a question?
No, sir.
Okay. Fine then. Then we'll upload this thing. I think it's already uploaded. So fine. I think then this week, since you have many other tests and all that, we did not have the live lab session. If you have queries, you put in the student discussion channel or email me. We'll keep on addressing them. So we'll meet again in the next Wednesday. But definitely read the stack frame part from that document that I was showing. Okay, it is already there in your set of materials for the course resources channel. So look into that and do accordingly.
Yeah, stack pointer manipulation and pushing arguments on stack and popping from test stack, using stack for recursive programs, etc. have been covered. Frame pointer has not been covered because for simple programs it's not that much required.
Fine, it's okay.
But yeah, I mean, please go through the manual once more. Understand more details.
Okay then. Thank you. We'll close the meeting then. Bye.
Thank you, students. Bye.
Thank you, sir.